I welcome you all in this lecture on methods of drawing bond graph models for electrical systems. So, next half an hour we are going to see how can we use bond graph in modeling an electrical system. Okay. This was the example which we have seen at the beginning of lectures on the bond graph modeling. Say a simple RLC circuit, a series RLC circuit if we take, and if we are asked to say draw the bond graph model of this system, then it is very simple. Okay. So, in this series RLC circuit you can see that we have a voltage source in series with resistor, inductor and a capacitor. So, as we have seen in methods of drawing bond graph, that first we identify what all are the different components. So, here we have a source, we identify the source here, a resistor, an inductor and a capacitor. So, this way we identify the sources and we say mark the how the power flows through these elements, all right, and then we put the constraint, and the constraint here is the same current through all the elements. So, I put a one junction here and then I causal it the usual way. Source voltage source will give an effort, resistor will take flow current and return effort, inductor will take effort and return flow, and capacitor will take flow and return the effort. So, this way we can draw the bond graph model of a series RLC circuit. Next, if suppose we have a parallel RLC circuit as here, again we have seen this example at the introductory lectures on bond graph. So, here are RIC are the circuits in parallel and these are subjected to a current source. So, again we identify what are the elements here. So, we have a source of current represented by source of flow, we have a resistor represented by R, inductor represented by I and a capacitor represented by C. Now, the constraint here is that all the elements are in parallel. Okay. So, that we put here by putting a 0 junction, which essentially means that the voltage across all the elements are going to be same. Okay. And then of course, as we have done earlier, we causal this bond graph. So, the current source will be giving current, so effort stroke will be coming here, the inductor will be taking effort and it will be returning the flow, a capacitor will be taking flow returning effort, and the resistor here will be taking effort and returning flow. Okay, and here we can see that this 0 junction is determined by the capacitor here. All right. So, these are the two simple cases which we have just seen, that is one is a series RLC circuit and another is a parallel RLC circuit. What happens if we go for more complex cases or complex electrical system? So, certain methodology need to be devised to take care of the modeling of the complex electrical systems. So, we will be seeing those methodologies. Okay. So, let us see. So, the bond graph of electrical circuit. So, the three methods have been found to be suitable in modeling of the bond graph of complex electrical systems. These methods are method of gradual uncover, point potential method and the mixed network method. So, method of gradual uncover, basically here what we do is that whatever complex part is there, complex series or parallel combinations are there, those combinations we try to make some sort of cover it, okay, and then draw the circuit, and at the latter part we try to uncover those parts. So, let us see. Okay. And these methods can also be extended for circuit morphic system, say in the field of hydraulic system or in the field of electronic system. I am not going to discuss these hydraulic and electronic systems here in this course. Those who are interested can read our book on modeling of mechatronic systems. So, let us begin with the method of gradual uncover. So, as the name indicates, the method of gradual uncover means that we are going to uncover the complex parts gradually, which has been covered earlier, okay, in order to simplify the problem. So, in this method one may cover conceptually comparatively complex part of the circuit and then treat them as macro impedances, fine, and then draw the bond graph putting such impedances at proper places. Then uncover them and put the details on the bond graph, and however, one may have subcovers covering complex parts of macro impedances which may then be gradually uncovered. So, this is what is done. Okay, to explain this concept, let us take an example here. Now, here you can see that we have a voltage source, a resistor R1, then we have some part here, say consisting of inductor I2, resistor R3 in parallel, okay, one branching is there, then we have the resistor R2, and then again we have branching consisting of inductor I3, capacitor C1 and R4, again these are in series and both of these are in parallel with I3, that combination is in parallel with I3, and of course then here we have C2 and finally here I1. So, you can see the complex nature of this circuit. Now, to draw the bond graph model of this, what we can do is that, as I said, here we can put a big cover here, as you can see the micro cover 1. So, such that we have the voltage source, resistor, this macro cover 1 and this inductor, they are in series, fine. And inside this macro cover again we can put a macro cover 2 here covering this inductor and resistor, so that these entities can be treated as one. Then I can also take macro cover 3 here consisting of this inductor and this combination as parallel, and of course this combination I can treat it as macro cover 4. So, this way you can see that I have made many macro covers in order to simplify my problem. Now, let us see how can I draw the bond graph model for such a system. So, here as I was telling you, if we look at this figure, so we have a voltage source SE, then we have a resistor R1, inductor I1 and whatever rest is there, that is macro cover. So, all these elements are in series, okay. So, I put a one junction here representing the constant current through all of them, okay, and this macro cover 1 is there. Now, what we do next, we uncover this macro cover 1. Now, for doing that, you can see that if I uncover this macro cover 1, then what we have a macro cover 2 here, okay, which is again this macro cover 2 is there, and then we have, and this 2 is in parallel with a resistor, capacitor and macro cover 3, okay, and again this resistor and macro cover 3 and capacitor, they are in series. So, what we do is that first we put a 0 junction here and put macro cover 2 and whatever these components are there, alright, this component, and then I open up this macro, I open up here. So, we have the R2, macro cover 3 and this capacitor in series. So, I put a one junction here, fine. After this I can uncover this macro cover 3, okay. And here in macro cover 3 you can see that we have inductor and macro cover 4 in parallel. So, here I just add a 0 junction, inductor and macro cover 4 are put over here, okay. And in next step we uncover the micro cover 4 also. So, here you see that this was the previous slide, previous model. Now, here macro cover 4 we have a capacitor and a resistor in series. So, here again I put a 1 junction and a capacitor and resistor I attach over there. So, this way it completes this one, okay. And further I can simplify this bond graph by say this 0 junction and this 0 junction, they are the neighboring 0 junctions. So, I can merge them, these two neighboring 0 junction, and this is what it reduces to I2 here and R3 here. So, this way we are able to draw the bond graph model of this complex system as this one, and this has been done using the method of gradual uncover. Next, let us see the method of point potential, okay. The method of gradual uncover fails in many cases, fine. For example, in situation like a bridge type of circuit. So, in bridge circuit, for example, a satisfactory scheme of creating covers becomes almost impossible. So, we need to find out some alternate way of drawing the bond graph model for such a system, okay. So, the alternative point potential method can be used to draw the bond graph model for this type of system. Now, in this system what is done is that each point of circuit where ends of various elements or sub circuits are tagged may be made into a 0 junction. So, each end or of various elements or sub circuits, those can be tagged as or made into a 0 junction. So, this is what is done in case of point potential method. So, then any element or impedance through which current flows may be attached to a 1 junction between the 0 junctions. So, this can be done, alright, and a suitable tag point may be grounded. This is achieved by attaching a 0 source of effort to a 0 junction. This means that the grounded point is subjected to a 0 volt, okay, and unless grounded the circuit remains floating. So, you should not forget to ground an electrical circuit, otherwise the circuit may keep on floating. Now, each individual circuits may be separately grounded. If there are many circuits, okay, then each individual circuit may be separately grounded. For example, in case of transformer, we have the primary winding and we have the secondary winding. So, these primary and secondary windings may be separately grounded, okay, on the both sides, and then we reduce the bond graph. So, this is the general method for drawing bond graph using point potential method. Now, let us take an example and see how this is done. Okay. So, this is our circuit. Say here there is a voltage source, there is a resistor, the ends of the resistor are A and B, and then we have the bridge here, and with the various ends say B, B, E, F, G, okay, and here of course other ends are formed B, C, D, E, F, G, H, I, and so on, and J here, the point J is grounded. Now, to draw the bond graph model for this system, as I said, first we identify the ends of the elements. So, say this resistor R, its end is A, so I mark 0 A here, 0 A, other end is B, so I mark 0 B. Then here this end is C, so I mark 0 C, this end is D, so I mark 0 D, this end is E, so I mark 0 E, this is F, so 0 F, G here, so 0 G, H here, so 0 H, and I here, so 0 I. Okay. Similarly, here the K, so 0 K, and L, so 0 L. So, this way it is marked, and there is a and J here, so we mark 0 J, and of course, yeah. Now, you see that after marking of these, in across these, in between these zeros point, we have the resistor R1. So, we put a 1 junction and attach the resistor R1 here. So, this is how it is done. Now, you see here between C and D there is inductor I1. So, C and D I put a 1 junction, and at this 1 junction I attach the inductor I1. Likewise, here I attach the resistor R2. So, I put a 1 junction here, attach the resistor R2. Here resistor R4 is there. So, between E and F 1 junction is put, R4 is put. Here between H and I 1 junction is put, a capacitor is put this side, and a resistor R5 is put that side. Similarly, between K and L inductor I2 is put here, and similarly other side between K and L resistor R3 is put after inserting the 1 junction. And here you see between J and A we have a voltage source. So, I put a 1 junction and put the SE element. Now, what we can do is that we can apply the ground here. So, SE is equal to say 0, I am applying here, and let us see how this bond graph gets reduced. So, in next slide I am applying SE is equal to 0 here. So, now you see that when this is subjected to the 0 volt, okay, so effort in this one is 0. Similarly, this is a 0 junction, so effort in this one will be 0. So, this bond will vanish, this bond will vanish, this bond will vanish, again this is 0 junction, so this bond will vanish, and this bond will also vanish, and again this is 0 junction, so this bond will vanish as well as this bond will vanish. So, let us see, we have SE here, here 0, same power coming and going. So, I can remove this 0 A. So, SE, and so I have 1 or R1 is here, then we reach this 0 B, and from 0 B, 0 B and 0 C I can merge. So, this is 0, then I can put 1 junction and attach I. So, I am doing it here. Similarly, I can put R2 here. So, from here I put a junction R2 here, okay, and so this is done. And then what we have here, D and E I can merge. So, this is here, and here this is 0. So, this has gone. So, at the E end I can just attach the what R4. So, here I can attach the R4. Likewise, let us see the other end. Here these two can be merged. So, here I have I2 at one end, and other end I have R3, and I reach here, these two can be merged. So, this one, and here I attach again these two can be merged. So, I can just attach C is 1 by C1 here, and similarly R by R5 I can put it here, okay. And here in between this G and E, this 2 I have R is equal to R6. So, this is how I reduce this bond graph into this form, okay. Next, this bond graph can further be reduced as you can see it here. So, we have SE, and then R is R1 is here, okay, and then this 0 junction is here, then this one, and here I have I and other R2. In fact, I can first find out the voltage difference across these two, and then I can put I and R here. So, this is what I am doing. I am putting I and R, both are going to subjected to the same voltage difference. So, I am putting a 0 here. So, this part is done. Likewise, I can do for this part here I and R, this is done, and then here I can come down R4 here, from here I can come to R6, and at this 0 I have C and R5 here, and this is what between this and 0 we have the R3, this already I have explained to you. So, this way we reduce this bond graph into this one. Next method is the mixed method. Now, in this mixed method what we do, we utilize both the concept, that is method of gradual uncover and method of the point potential. So, the method of point potential and gradual cover may often be mixed for the great advantage, and the complex impedances may be covered in the first go, and once the overall structure is produced by point potential method, then the uncovering may be taken up, okay, and the ultimate bond graph may then further be reduced using the conventional reduction principle. So, let us take again the same problem, and now this same problem I am going to do with the help of combinations of gradual uncover and method of point potential. So, here you can see that what I do is that this complex part I can put under macro cover 1. Okay. Likewise, this complex part I can put under macro cover 2, and this part I can put under macro cover 3. So, here what I am doing is I am applying the method of gradual uncover, okay, by covering these components, okay. And let us see now we can go for the method of point potential. So, I identify the potential at point A as 0A, B as 0B, okay, and here C as 0C, E as 0E, D as 0D, okay, and now across the elements, okay, across the 0 junctions I attach in between one junction and attach the element over there. So, for this R1 I put a one junction, attach R is equal to R1, and similarly between B and C I attach a one junction and put a macro cover 1, and B and D I attach a one junction, put macro cover 2, and between D and D I attach one junction and put macro cover 3 over here, and rest of the things are same, putting of R6 and R4, alright. And here this F is subjected to a 0, it is grounded, so we have to put the 0 voltage across here. Now, you see that I can apply the method of gradual uncover in order to uncover the part 1 and 2 here, 1, 2 and 3 here. So, what I had is I will do certain simplification in the bond graph also. So, let us start from here. So, SC 1 is here, this 0A can be eliminated because same whatever power is in, the same is out. So, I remove this 0A. So, I have R as R1, then I reach here 0B, and then between B and C, say this is 0B and this and C I put 1, and then C and E I put R4, and E and D I put 3, and between say D and B I put 2. Okay. So, this is what I do here, fine. And then after doing this, what we can do is that we can apply the uncover method here to uncover these 1, 2 and 3. So, this part 1 I can uncover, 2 I can uncover, and 3 I can uncover, and here. So, this is what I can do here. Uncovering means these are in parallel. So, I put a 0 junction and attach I1 and R2 here. Okay. Likewise, here I can put a 0 junction and attach I2 and R3. Likewise, here I can put a capacitor of capacitance C1 and R5, and this way I am able to draw the bond graph model for the same system using the method of using the mixed method. Okay. So, this can be done. Then let us take an example for say modeling of an electrical motor, alright. So, this is again a modeling of an electrical system which we often come across, Okay. So, suppose here this is a motor which is subjected to a voltage say E or say V in, and say current through this is I, and we have a shaft here from where we get a torque T at angular speed omega. Okay. So, these are the constitutive relationship which we see. Torque is I into mu, and this voltage will be mu into W. All right. Now, if we look at say the bond graph model of this one, so armature I can take it as a inductor resistor in series with the voltage source. So, I draw I, R and SE here, and this relationship basically the torque and current are related by a torque constant of the motor. So, this mu I model with the help of a gyrator element, okay, and here is basically my this torque, and here is my omega. Okay. So, that is there, and of course, here at the end I put say the inertia of the rotor, and here I attach a resistance representing the bearing resistance, and here I can put some sensor here to sense the say rotation. Now, in this bond graph you see this is my say I, this is my R, and this is my SE, and here is my GY, and here is 1, and this is your I, and this is your R. So, this part is what we call is basically the mechanical part, and here is your electrical part. This is mu, and this will be actually torque, okay, and here say this is E and I in the electrical side, and torque and angular velocity at the mechanical side. So, from here you can see that the tau will be equal to mu I, and here E which will be the back EMF basically, that will be mu times omega. So, this is what is going to be, okay, and then we can generate the system equation for this system, and we can write the system equation. Another example here, it is a basically sensor and actuation both can be modeled here, or this is explained with the help of concept what we call it as the activation. That is by activation what we do is that we make a power bond as a signal bond. So, what we do, we suppress one of the power variable either effort or flow in order to make it as a signal bond, and such signal bonds can be used as a sensors, okay, in your modeling. Okay. So, these bonds are not power bonds, and such bonds when where one of the factor of power is masked are called the activated bonds. So, suppose we have a spring mass damper system, I want to say put this mass at a certain position, then I put its velocity using as a velocity pickup, I amplify that velocity, and then I apply a force on this mass using an electromagnetic exciter, so that I am able to say keep it at certain position. Okay. So, to model this entire system, what we can do is that we take a one junction representing the velocity of the mass, other end of the spring and damper are fixed. So, they will be having 0 velocity. So, here I just put I inertia, then spring and damper, and here you see that they, what we are seeing here basically a velocity or flow is being converted into effort. So, we can use a gyrator element to model this type of system. So, here you can see that effort is 0 from this bond. So, that is this is carrying the flow only, and then we amplify, and that amplification is represented by modeling the putting the modulus of gyrator as mu, and then it is applying a force here. So, again here we activate it for effort, that is effort activation, that is effort goes and flow is 0 here, and so this way we can model using the activation of the gyrator element this velocity pickup and the electromagnetic exciter. Okay. The same concept we can use to make a C element as a displacement sensor, and by flow activating it and by effort activating an I element, we can make it as a sensor for the force. Okay. So, that is all here. Thank you.